Alright, welcome back. This video is going to be an introduction to the techniques used to solve frame and machine types problems. Now if you remember our listing of how we start to tackle problems, we started out looking for ropes and cables, and then we moved into two force members. And so the third step now is going to be looking for frames and machines, and we'll show you how to kind of tackle those. Now there are a lot of different types of frame and machines. Basically, if it isn't a truss and it's pinned in any way, it's classified as a frame and machine. Now this includes things like hand tools, pulleys, as well as articulated mechanisms used in mechanical engineering. So we'll kind of show you some of the strategies for how we do it. Now it has a lot of the same steps that you've already seen. Okay, the first step is always drawing a Freebody diagram of the entire system. We're not going to blow anything apart, okay, because what that does is that keeps us from exposing internal forces at the time, and maybe we get lucky and maybe we can find some of the support reactions. Okay, it's not always the case, but we want to try to find what we can without going into any of these more complicated methods first off. All right, once we do that, then if we still don't know everything, then the technique is going to involve basically separating the system into smaller subsystems that we're able to analyze individually, and then we can use information gathered from that to reconnect it and establish solving for other unknowns. And I'll show you a short example here in just a second. This method is very, very handy, and a lot of the tricks that you see here become very, very popular in more advanced classes like structural analysis or machine analysis or something like that. All right, so what we're going to look at for this particular example, okay, is we're just going to take a fairly simple system, all right? And if you look, what we have here is we have a couple of bars. This is a very, very simple system. It's a bar that's from A to B, it's pinned at B, and then another bar that goes from B to C that's pinned at C. And at first look, it looks like, hey, this would be a truss by our very definition, right? Remember, it's a straight member pinned at the ends, okay? But what it violates is it violates the assumption that all loads are forces, and those forces could only be applied at the hinges, all right? So it could only be applied at A, and it could only be applied at B. So if we look at this member, I have a moment here. This guy is clearly not a truss member. So we know that the forces in this are not axial only, okay? And in fact, this guy will have some bending because this thing's trying to kind of bend and kind of trying to rotate that particular member, right? And then likewise, over on BC, I have a point load that's out in the middle. It's no longer out at the ends, at the hinges. So this guy also is not a truss member. Okay, now I can have truss members connected to hinges. In fact, if this load P were not there, this guy would be a truss member. I know he would have to be an axial load. Okay, so we can always kind of fall back on pieces. So the whole system doesn't have to be classified as a frame and machine or a truss or whatever, but the individual pieces that we're looking at. Okay, so we're looking at two pieces, one from A to B and the other from B to C. Again, B is a hinge. Okay, so first thing I do is I draw the Freebody diagram of the entire system. And what you see is I've got a pin support at A, so that gets me an AY and an AX. Okay, and then I have a pin support at C, that gets me a CY and a CX. And then I have my applied moment and I have my applied force P. Again, we're looking at Ys. There's no mention of self weight. There are no internals because I didn't cut anything. So all we have are support reactions and the two external, the external loadings that are happening on this. All right. Now the problem that we have with this particular system is that if you count the number of knowns, assuming that we know M and assuming that we know the value of P, I have four unknowns: AY, AX, CY, and CX. That's four unknowns. But this is a two-dimensional problem. I only have three equations, right? I can only do sum of forces X, sum of forces Y, and sum of moments. All right, so this isn't solvable. We have four unknowns and only three equations. This is statically indeterminate to the first degree. All right, and so this will happen a lot in frames and machines, but we can still work with this if we apply some of the tricks for this particular methodology. And so the main thing that we're going to do as we start to kind of look at most textbooks, I'm going to show you first the kind of the way that most general textbooks start to attack this problem, and then I'm going to show you kind of where that thought comes from, and we'll show you a more general approach. So let's do that first, and we'll kind of start to work our way up here. All right, so all we do on this, okay, for a system of two, and this is, like I say, some textbooks get a little bit confusing when they do this, is we're going to take a look at the hinge, okay? The trick to frames and machines is we're going to blow it apart at the hinges. All right, so if I take that same system, see, I'll pull this down a little bit so you can see the original, right, is I have my member from A to B, I have my reaction AX and AY, and my applied moment on this case, okay? And so what we know is that because this thing is hinged out here, there is no moment at that location, okay? But it is restraining the end of the member from moving in the X direction and moving in the Y direction. So if I were to show those two unknown forces, because that's what a reaction force is a resistant to a motion. Clearly it's being resisted in the x direction, it's being resisted in the y. Okay, and so the idea is that if this bar pushes on the pin, then the pin has to push on the other bar, which means that these two guys are equal and opposite. So whatever I assume here, bx, has to be applied in the opposite direction on the other side. Okay, and likewise in by, if this one's coming down, then this one has to be up. And so for two members coming together at a hinge, these are equal and opposite. I mean, if you look at the joint, remember we got to maintain equilibrium everywhere, right? And so I have a bx to the right, a bx to the left, that's balanced. Okay, and I have a by down and a by up, that also is balanced. So the net effect is 0 on the pin at B. Okay, and so what happens then, okay, is we have two valid free body diagrams up here. In fact, we have three, but that's a 0 equals 0 case. All right, and so what we can do is on this first piece is I can now go in and I can find sum of forces x, sum of forces y, and sum of moments equal to 0. That gets me 3 total. All right, and we can write that. We've done that before, in earlier chapters. It's nothing new, nothing special. Okay, and then I can go through, but when I split it the way that I did, I get a second free body diagram over here. And with this guy, I can also write 3 equations. And so I can do forces x, forces y, and moments, and I get 3 total. Okay, so now I have 3 equations here and 3 equations here, give me a total of 6 equations. Okay, now, by setting this problem up this way, remember we had 4 unknowns originally. I had the AY, AX, and CX, CY on here, but now I've added in BX and BY to the picture, right? So total unknowns is I have 4 unknowns on here, and I have 4 unknowns on here, but the 2 guys that are up here at the pin location are the exact same value. So really, instead of 4 unknowns, it's only 2. So total is 2 plus 2 plus 2. I have 6 unknowns on this entire system with the 6 equations that I write. Okay, and so our unknowns are AX, AY, CX, CY, and then of course the pin forces BX and BY. So 6 unknowns, 6 equations. The system's now solvable if I blow it apart this way. Now again, we've got to be very careful, and the main trick to solving these is finding these unknown internal pin forces, these BX, BYs, because when I separate it apart, I get a new set of equations that I can now write for that particular free body diagram. All right. Okay. Now there is one problem that we should point out. Okay. Like I say, most textbooks, this is the approach they do. They say put a force on one member and then take the same force and put it on the opposite. All right. I'm going to show you where this idea comes from. All right, because it kind of opens us up to some other pieces. So all right. So if I take that same basic frame that we have on there, right? This would be our picture, right? Okay, here's my A, here's my B, here's my moment. And so all I'm going to do is I'm going to call, AY, AX are the same, M is the same. I'm going to call the force up and to the right. So we're doing a right-hand rule sign convention. That's the convention whereby I put an X and I put a Y and I put a positive moment there. That's my positive sign convention, if you remember. All right, so everything I've done is I've assumed positives on this. Okay, and so since I know there are forces at this hinge, I know that there's no moment. Okay, but I do know I have a horizontal force. I do know I have a vertical force. I'm going to call this guy BX1 and BY1. Okay, and then over on the other piece, I know that he's pushing, even if I don't realize that he's related to this, I know on this piece he's also restrained. And I'm going to call that BX2, BY2 on that. Okay, and then CX and CY, of course, for this particular system. So that's the basic picture that we have happening. But the thing that connects it all on there is what's happening to the connector element, okay? In fact, the connector element between all this is that little shear pin that's going through and kind of holding those pieces together, okay? And so if I do that, if we maintain equilibrium of the pin, this guy pushes on the pin and the pin pushes back. That's one of Newton's laws, equal and opposite reactions, right? So if I'm pushing this way with BX1, then the pin has to be pushing back with the same BX1. So that's why this BX1 is in the opposite direction. And then BY1, since we assumed it's pushing up, then the pin is pushing down on the member as a response, okay? So that's these two guys. But this pin is also being affected by what's happening over on this member, right? And so a BX2 to the right, okay, becomes a BX2 on the pin to the left. And a BY2 up becomes a BY2 on the pin that's left, okay? And so now we've got a third free body diagram, and this guy is completely valid, right? And so if I write my equations for the pin on there, I can do forces x, and I get the equation minus bx1 minus bx2 equals 0. This tells me that bx1 is equal to a negative bx2. All right, and all that says is that, okay, the magnitudes are the same, but the directions are different. That's the presence of that minus sign on bx2. Okay, now I don't know, maybe bx1 is negative, makes bx2 positive, I don't know. That doesn't really matter, but the idea is that they're equal and opposite, which is what the textbooks, most classical textbooks will show you. All right, and do the same thing in the y direction. I get minus by1 minus by2 equal to 0, and now by1 is equal to a minus by2. Okay, so even the up and downs are opposite, and that's exactly what we saw on that previous example. Okay, where this method starts to fall apart, and they try to sneak this in on textbooks, and Beer & Johnson does this as well, they have a couple of problems where instead of 2 members coming together, it's coming to 3. And when that happens, the idea of equal and opposite doesn't work anymore. All right, so what we're going to do is just kind of real quickly, I've taken just an arbitrary member here, system with 3 members, number 1, number 2, and number 3, pinned together, sharing a common pin. And we're going to apply the exact same strategy that we saw up there when we were dealing with 2 members. All right, so here's my free body diagram for number 1. And again, I don't care what's going on down here. I'm just looking at what's happening at the pin. I mean, there could be a load on this thing. There could be forces, moments. I don't care. Again, I'm just kind of exploring what's going on with the pin, how the pin affects the member. All right, so all we do is do bx1, by1, pushing on the pin, and that's these 2 guys opposite, right? Exact same thing that we did. And then I go in and I look at number 2. Here's my pin on there, and now I go bx2, by2 on number 2, and his opposites are these 2 guys in the middle. And now with the 3rd member on there, I get a bx3, by3. All right, no tricks here. And so bx3 is to the right, by3 is down, and so this becomes the free body diagram on my pin. All right, and if I write my equations for that, it gets a little bit more complex. Get this up here where you guys can see it. All right, and so if I do forces x, now I have minus bx1, minus bx2, minus bx3 all equal to 0. Okay, so all that says is it says that all of the x direction forces coming into that pin have to sum to 0. Now, when there was only 2 of them, that's how we knew one was equal and opposite to the other. But when there are 3, instead, these 3 all have to total 0. So if this guy is 200 and this guy is 400, this guy is going to be 600 in the opposite. Because again, this plus this plus this has to sum to 0. All right. So, and then likewise for the y direction. So that becomes one of the tricks. And so I don't like to use that idea that, oh, well, to tackle frames and machines, it's always equal and opposite on every side, because it's not. It's only that case when you're dealing with 2 members. That's the way I learned it, was 2 members equal and opposite. But it wasn't until later, after I got some more experience dealing with more complex systems, that this is actually the truth. Okay, it's a more specific requirement than that one that only works for a 2-member case. So now you have the tools to be able to do that. All right. All right. So we'll get our page flipped over here. Okay. So now we can have more complex systems. Okay, if you remember trusses on here, I apologize, that's a little small, but I think we're all right. Okay, is that trusses required pieces to be connected at the ends. Well, maybe when I get to a frame and machine, if we identify that the members are still pinned at their ends for the most part, I can do some even more advanced things. So let's suppose that I have that same A-frame happening with a member that goes from A to C. It's one single member. I know it looks like it's 2, but it's not. It goes from A to C, and then in the middle of this thing, I pin this horizontal guy to B. And then likewise on C and E, I pin the middle guy on D. Now, this particular example, we have a pin connection, and then I have a roller at E. Okay, so all we want is just a little bit of practice in drawing our free body diagrams for being able to do this. Okay, and so just like we did before on here, is that we go in and we start to draw our free body diagrams. Now, if we look at B, we draw it for the whole member. I don't cut the member, I only cut it at the pins, right? If I cut it here, cutting across this guy, then all of a sudden I get a whole bunch of internal stuff that shows up, and that makes our problem a lot more complex. And when we get to internal forces of beams and things like that, I'll show you how to handle that particular case. But for this, we just want to cut it at the pins. That's the trick here for frames and machines, is find the pins and cut it apart at those locations. So AY is a vertical reaction, AX is a horizontal reaction. Okay, now we're going to go back to the old classic that, hey, I got 2 members. I know that if I assume, to the right and down are BX and BY on this guy, then on the end of B, I have to do the opposites. So you see it was down BY here, it's up BY here, it was to the right BX here, it was to the left BX here. All right, and so if I draw my pin, we get back to our old favorite of that. All right, and that's clearly, if this is BX and this is BY, okay, and this is a BX and this is BY, that pin is clearly in equilibrium. It's the same game that we just played. All right, and then if I go over and I look at D, I can do the same thing with this, right? So if I do dx to the right positive, dy up positive on here, on the member that he connects to, even though it's not at the ends of the joints, I can still put that force at the hole that's in the middle of the bar. All right, and so dx is to the left and dy is down, but again, equal and opposite. So I go up, here's a dy, and then the other one was acting down, and then over to the right is dx, and then over to the left is dx. Those are the forces that are acting on the end of this bar as well as the end of at the hole location on the diagonal. All right, and you can see again, it's an equilibrium, no major surprises for us there. Okay, the other piece then is that we also know that C is connected to the other C. All right, so if I do Cx to the right here, I have to have a Cx to the left here, and if I do a Cy down here, I have to do a Cy up here. Okay, and so that gets us our particular setup for this. All right. So again, if we draw our joints, right, the net effect at joint B is 0, the net effect at joint C 0, and the net effect at joint D also 0. So we're in great shapes. So once I do that, now I can go in and just like you did before in the previous example, we can write an equation for member AC. All right, and so our member ABC, we would get 3 equations: the force is X, force is Y in a moment for him. And then I would get another 3 for that horizontal BD member. All right, so that gets me 3 more equations. All right, and then CDE, likewise, I get 3 more equations. So I get 9 total equations on this thing. Okay, now if we go in and we look at the total number of unknowns that we have, I've got AYAX 2, BYBX 2, that's 4, CYCX gets us to 6. Okay, and then I get dy dx gets us to 8, and then I get this extra reaction ey gets us to 9. All right, and so our whole system on this is 9 unknowns. So even though it's a fairly complex system, I now have 9 equations and I have 9 unknowns. We can solve this system. All right, okay. All right, so let's give one a try. Okay, so now we can have all sorts of complex loadings as we start to kind of look at our frame of machines. Okay, and so here's our picture. We have a fixed in support here with a member that goes from A to B, and then I'm putting a hinge here. So some sort of articulated setup. I have a point load in the middle that's kind of at an angle, and this is, like I say, it's a little hard to see. It's a 3, 4, 5 triangle, okay, and the amount of 10 kilonewtons, and then I have 4 kilonewton meters on this last segment that's 2 meters long, and then I have a roller support at C. And all we want to do for this system is find our support reaction. Okay, all right, so if we go through and we look at our particular supports on this thing, okay, we know that the roller is a single vertical reaction, and I know that a fixed support, if you recall, was a moment, a shear, and a normal acting at that location. All right, so if I apply that to the system free body diagram, again, you draw this free body diagram for everything, okay, you get a picture that looks something kind of like this. All right, so at A, I have a vertical AY, a horizontal AX, and a moment MA. Okay, I get this force applied at a distance of 2 meters. So let's get some dimensions on here. So that's 2 meters, and this guy is also 2 meters. And then this guy is also 2 meters. Okay, now clearly, well, before we get into this, let's get the rest of this on here. I have a 4 kilonewton per meter force on that distributed load. Okay, and then I have my single reaction CY. So we have 4 unknowns, okay, and we have a hinge at B. All right, and so this hinge is that kind of our secret to how we start to solve this problem. All right, 4 unknowns, 3 equations for the whole system. I can't find everything. Now, I might get lucky and be able to find one. In this case, I can't, but on some problems, you sometimes get a little bit lucky. All right, so all we're going to do is we recognize that on our system that it wasn't a truss, right? And, okay, because this is fixed, so that's clearly not a truss. And this guy was pinned here and rollered here, so that was kind of met that requirement, and it's straight, but the problem is that this load is not loaded only at the hinges. All right, and so this guy goes into some sort of flexural case, and so we've got to be able to go into that. All right, so all we're going to do is we're going to break this thing into pieces. All right, and so I have, you know, my moment, MA, AY, AX. I'm going to blow it apart at the hinges, just like we did. And so we have 10 kilonewtons, and then 3, 4, 5 is the angle. Again, that's located at 2 meters, so we're good there. Okay, and then I'm just going to assume a couple of directions. Again, I don't know which direction is correct. We're just going to assume So for the sake of this example, I did bx to the right positive, I did by down positive. Okay, and since this is only two members connecting it, then whatever's happening over here has to be opposite of what I drew here. All right, and so if I did bx to the right here, then the bx on this one is actually, I have it drawn wrong. Okay, would be a bx happening on that guy, and then the by has to be opposite of this one, right? Okay, then you get your cy reaction over here, and then we get this distributed load guy. And so if you remember, we have a distributed load of 4 kilonewtons per meter for 2 meters. All right, I get a total of an 8 kilonewton force acting at the centroid of the load pattern. Now, if you recall, this was a rectangular uniform distributed load, so the resultant of this load would be acting at the middle of that. All right, so in that case, it would be 1 meter from B and 1 meter from C, which is what you're seeing here. All right, so this becomes the equivalence of that distributed load. So you can see we're starting to do some fairly complex calculations, not just simple point loads anymore, as we start to kind of work with that. All right, now, one of the challenges in this particular technique is that I now have my two free body diagrams drawn, and again, our hinge is at equilibrium. So if I did this, this would be by, and then the opposite is by, and then I do bx, and the opposite is bx. All right, so clearly that's an equilibrium. That's the effect of this guy and this guy acting on that pin. All right, now if we look, the question becomes, well, where do I start? I've got a whole lot of information, and we've blown this thing apart, and we made kind of a mess out of things, but you can kind of look at the equations and go, well, if I look at this picture, I have the 3 unknown support reactions plus the 2 pins, that's 5 unknowns. Okay, well, I've only got 3 equations, so that's probably not my best bet to start. But if I can find bx and by, then I can pick off these guys. If we go over and look at the other piece over here, you'll notice that I've got bx, by, and cy as my unknowns. The load we know and its location, that's only 3 unknowns. This guy is now a solvable system. Right, and so I can solve for everything I want on this. I can find cy, and then I'll use that to find bx and by. And when I find those, then I can come back over here because now I know these two guys. And with those two out of the way, that gets me 3 unknowns, and I can solve for those. And that's kind of the general progression of a frame and machine problem. All right, so if we go through and we do this a little bit, let me see if I can get these pictures where we can kind of start to still see stuff. How's that? I think that will get us pretty close. All right, so if we start to look at BC first on here, right, I can do sum of forces x equal to 0, so bx, and again, we're looking for segment BC, so we're looking at this picture over here. So the only thing acting in the x direction is this guy, so bx is clearly 0. All right, and then I can come in and I can look at, well, let's do the moment about B on this particular picture. On there, all right. If you can kind of see it a little bit. There we go. Okay. Moment about B, we're going to go counterclockwise positive. Okay, and so I can take my 8 kilonewton force that's here, that's acting at this location, okay, and when I do that, I multiply it by 1 meter, okay, and that's wanting to go this direction, which is clockwise, and that's opposite of what is in positive, so that's a minus 8 times 1, okay, and then plus cy times its 2 meter guy will get me 2 meters here, equal to 0, and so I can find out that cy is a positive 4 kilonewtons, solves this equation, and positive means what I drew here is correct, that he's actually acting up, so cy reaction is 4 kilonewtons up, all right. Once I have cy, I can write the Fy equation, which is this next one down here, this Fy guy. Okay, and if I look at my picture, that gets me a By up, it gets me a minus 8 down, and a positive Cy ups. And so that's what you're seeing here, By up, minus 8, positive Cy, all equal to 0. But I know the Cy was a positive 4. All right, so if I write this as a positive 4 using the sign of the value, oh, I know it looks like a 9, but use your imaginations. Okay, positive 4 minus 8 plus 4, then By in this case is going to end up being equal to, in this case, a positive 4 kilonewtons. All right, and so the positive 4 tells me that By on this case is correct. All right, now we've got to be kind of careful here because I can't really put an arrow on him because By is actually an internal force, right? If I put a By up on this guy, I would be violating what's happening here. So we're going to say that it's a positive 4 associated with the way that it's drawn on these pictures. Okay, so that's one of the challenges. It's kind of like that issue that we got into with trusses with tension and compression, how different ends of the thing were opposite signs but the same magnitude. All right, so once I have that though, then I can go back and now I can start to look at for segment AB. All right, so let's see, can I pull this up over the top? All right, and we can start to kind of play the rest of this out for us. All right, so for segment AB, we can do sum of forces x equal to 0, and so I'm going to take AY up, or sorry, not AY, AX, and AX to the right, okay, and then plus my BX to the right that we had happening here. Now we know that this guy was a 0 value on there, okay, and then I have my horizontal component of this diagonal 10 kilonewton force. So if you remember with proportions, it was 3 horizontal, 4 vertical, 5 diagonal. So his x component is going to be the horizontal piece, 3 over the hypotenuse, the 3/5 of 10 kilonewtons, right? And so I can do minus 10 kilonewtons here, 3/5 of that gets me the x component, and then the minus sign tells me that his component is acting that direction to the right. Okay, and I can go through and I can solve that. Now, we know that bx is 0, and so I can find out then that ax is actually a positive 6 kilonewtons. We'll satisfy that equation, and so we know that if that's my 6, okay, that his force would, external reaction would be pushing to the right on this thing. And that makes sense, right? Because I got that force that's kind of trying to push this bar to the right, then ax is clearly going to be trying to resist it coming back this direction. Okay, all right. We can then go in and do MA. And so I have my MA force that we're going to do, again, counterclockwise positive. So we assumed it positive on the reaction. Put this down a little bit. There we go. So we can see stuff. Okay, and then again, we're going to take the moment that this guy creates. Now the x component is acting, we're assuming, at the centroid, so it's going through that point. So there is no x component. The vertical component is acting down at this point, right? And so I can take the vertical component, which is 4/5 of 10. So you see the 10 and the 4/5, and then it's acting at a distance of 2 meters, and it's wanting to go clockwise, so that's why it's a minus. So minus 10 times 4/5 times 2, okay, and then I have my by. Now notice this by is down. We assumed it positive here, so I'm going to use it the way I drew it on this picture, with my by acting down, okay, and so this guy times his 4 meters is going to be a clockwise moment, so that's why he goes in as a negative. All right, and when I do that, I can do the math, and my MA then ends up being 32 kilonewton meters. It ended up being a positive value on here, which means that the direction that I assumed, counterclockwise positive, was correct. And so your final answer for MA is 32 counterclockwise in that direction. Okay, and then finally, the last picture, we can come through, we can do sum of forces in the y, and so all of this is fairly easy. It's AY times that y component of the 10 kilonewtons, plus the by. So AY is my unknown, minus 10 times 4/5 again, minus BY all equal to 0. AY is now a positive 12 kilonewtons acting upwards. All right, and so now we've got all of the support reactions for this particular picture. That's all there is to it. It's just a matter of kind of starting on one piece. In this case, we started on the piece that was over here, solved for a bunch of stuff, and then I moved over to the other piece. Okay, now as these systems get more elaborate and you get more pieces coming together, sometimes I solve for something here, I jump over, get something, I come back, and you can end up going, it becomes a bit of a logic puzzle to figure out how you progress through the system. And in the next example problems, I'll show you some more cases. We'll work another example that's a little bit more, not quite so trivial, but for illustrating the setup for how we tackle frames and machines, this I think does a pretty good solid job of it. All right, so again, you're looking for hinges and you're blowing it apart at the hinges, and you're playing with the pin forces and how they act on the members. Okay, so again, we had 2 members here, that's why BX's were opposite and BY's were opposite. If I had a 3rd member coming in, we would have to play something a little bit different, and I'll show you that a little bit later. So anyway, I hope this kind of explains it clearly enough for you. Give me some feedback. Let me know if you have any questions on this. Post in the comments. If not, we'll see you all next time on our next frame and machines problems. Anyway, thanks a lot.